Well, hello everyone, welcome back, and today we will do something interesting, and we will try to enter a syscall with the debugger, and we'll be using a little bit of a kernel binary patch. And well, let me show you what I'm talking about. So first of all, I'm working in a VM, as you can see, and I will also work in my host machine because we'll be dealing with the kernel code. But first, a few days ago, I've written a blog post about the cost of a syscall in Windows. It's a very thorough breakdown of all the things that happen inside the syscall. And by the way, all links will be in the description, so you don't have to memorize any of this. So if we kind of go quickly into the syscall itself, you've noticed probably many times in the user mode, if you are reverse engineering, that when you get to a syscall instruction, it gets executed, and even if you try to step into it, like you would, let's say, with the call instruction, nothing will happen, and it almost looks like an atomic instruction, kind of like a monolith one. Well, indeed, it is not. So the kind of like blog post below kind of describes what was happening. Now, first, before we begin, let me explain how, what I'm doing here and how how I set up my my work environment. First of all, as you can see over here, I'm working in a VM, again, like I explained, because we will be dealing with the kernel code and we will have to freeze the operating system. So ideally, it would be nice to work with the VM, but you can use an outside computer. And first of all, I need to kind of like give you another link. This is my previous blog post, how to set up a virtual machine for my reverse engineering work on Windows. Now again, link in the description. This blog post will give you all the details needed. So again, this is what is happening here, like all of these things. Now, we won't be using all of the apps. We will probably be using just IDA. But overall, this is where you can get it. And then the third one that you will need, also another blog post, is to how to set up WinDbg. I'm using the new version of WinDbg because I like it over the old one, but I guess you can use the old one. But this whole blog post is how you can set it up using the fast network connection, which, by the way, the old WinDbg doesn't support, and this is one of the main reasons why I will be using WinDbg Next. Again, link in the description. Follow this blog post, how you can set it up on the host machine to actually do all the work. Okay, well, before we go any further, we need to kind of see what we're doing. Now, in my blog post, if you scroll up, you will see that I'm using this API to kind of demonstrate the syscall, and this is wait for single object, or NT wait for single object if you kind of like dig deeper into it. So if we look at the actual Win32 API, let me just open it. Let's see. Oh boy, yeah, this browser is not very friendly. Okay, so if we look at the documented Win32 API, this is wait for single object. And this is what I was actually kind of like torturing here in my blog post. And kind of like in the same vein, let me continue it. So we need to see basically what happens inside and how did I get to all of this stuff, right? When I got to the actual assembly code that is executing in the kernel, well, how did I... Oh, sorry guys, yeah, this browser is just pissing me off. But anyway, now how did I get to all this code in the kernel? So for that, we need to write a small test project that we can use to actually call this function. So I'm usually using Visual Studio, and I create a simple console application, C++. It doesn't really have to be anything fancy. And let me just call test syscall. And this will be a very basic C++ app. We don't really need it to be C++, to be honest with you. Let me add a little bit of the font size here. So again, I won't be writing a lot of code here. So basically, we just need to call this instruction, this function. And if you see, it needs a handle. And let me see, we'll wait for infinity basically, and we need a handle. Well, the easiest one is just let's create an event, and we don't have any attributes, doesn't have to be manual. Okay, now initial state would be false, right? And the reason you would do false is so this wait instruction basically waits forever. And let's be good citizens and actually close the handle. So this is the entire app. So if we run it and put a breakpoint here, as you can see, it goes into infinite loop because we basically gave it event that is not signaled. So this wait instruction will wait forever. And the way it does so, it goes into the kernel. So this is technically all we need. So let me build a release, kind of like optimized build, and let me find it. And it's over here, and technically if we run it, we'll just hang. Okay, this is correct. Okay, so at this point, let me move it to my virtual machine. And I will put it into reverse engineering folder. And let me just call it test SYSCALL. Okay, so let's make sure it runs, and it does. Again, not very interesting app. Well, first of all, let's see what happens internally. So again, if I open it in the user mode debugger, at this point, again, nothing interesting. So just kind of like, basic stuff. We don't have symbols. Again, I'm going to go through this real quickly because, again, you can kind of watch my other tutorials where I explain all this stuff. But basically right here, as you can see, we have a main function, and then we create event. Then we call wait for single object, and then we close it. Pretty much exactly all this stuff here, except, in a binary form. Well, let's kind of like step into it and see what is happening internally. So I put a breakpoint, and let's go through all the warnings here in IDA. Okay, so let me step into it again. Now, if you know the step into instruction is this one, execute each instruction. Again, it depends on every debugger. But basically, you can step into, like in this case, call instruction. And if you do so, as you can see, we stepped in. Let's do it one more time. We're inside of kernel base. Again, not interesting, just a bunch of shims. They jump from module to module. Yeah, Microsoft seemed to like doing this stuff. Okay, and we are inside of kernel base. Now to make it more readable, let me load symbols here. And I have to let IDA do its thing. It's a little bit slow. And let me analyze it in case, I'm not sure if it's doing it automatically, but probably not. Yeah, IDA free, maybe the paid version does it automatically, but there's a lot of manual things and it kind of takes forever. You see, like, I basically look at the bottom and it's doing something. It means, just sit and wait pretty much. Okay, so let me look at the call tree. Okay, and let's step through it. I'm gonna go really fast. And what I'm looking for is the internal instruction. So internal call to NTDLL. Right now we're still in kernel base, which is kind of like an auxiliary module. So okay, and over here, as you can see, this call instruction actually takes us to NT, wait for single object. This is the native function call. So if we step into it, and we hang the IDA. Okay, guys, sorry. Okay, so we're inside of NTDLL, and this is where the magic happens. So if you look over here, well, first of all, let me put a breakpoint so I don't have to do this again. Okay, if you look over here, if we step in, we get to the SYSCALL, and this is exactly my example over here. You see this is a SYSCALL, and if we try to step into it, well, in this case, our app hangs up because, you know, we stepped into it and we never came out. It's just basically, it acts as an atomic instruction in this sense. So let's stop the process, because obviously we will never return, because, you know, our event, well, will always be non-signaled. And the question is, how do we get into the kernel side of the question? So if we go into my blog post, and the first thing that I explained is what happens inside the syscall instruction, right? Because the syscall instruction is a CPU instruction, and if we read, again, you can go to and read the Intel documentation, or you can read my synopsis here, but basically it does a few changes here, but in our purpose it's not really important. What is important is RIP register. Now RIP register is the instruction pointer in 64-bit, and this is where we actually jump to the kernel. Now if you read the documentation, it's using this L star MSR, and MSR is internal register on Intel and AMD CPUs, kind of like the ones that are not accessible from user mode. But from this MSR, which is L star MSR, it contains RIP, and this is where it jumps to. So how do you get to it? Obviously you can't get to it from the user mode debugger, but you can get to it from the kernel debugger. Well, in this case, what we need to do, I need to create a new notepad. And if you remember, I was using it as a sort of a scratch pad for my work. And in this case, I will be using my host computer. And I will copy this whole thing, because I will actually use it in the kernel debugger. Okay. So this will tell us the MSR that we will need to actually look into. Okay, well, at this point we are ready to connect to our client guest operating system and break into the kernel. So I'm using WinDbg Next on my host machine. And again, please refer to my other blog post how to set it up. So if you want to connect to the kernel, again, after the setup, you go attach to the kernel. And you need to set up these parameters like the port number. In my case, I chose totally arbitrarily this port 50,000, 500,030. Again, read the blog post and how you can set this thing up. But when everything is done and ready, if you click OK, the debugger will try to connect, and it will break inside the kernel. And the reason you can see that it broke inside the kernel is because nothing works in the host in the guest machine. See, it's completely frozen. Okay, well, if you remember my previous explanation, we need to get to this L star MSR that contains RIP. Now in this case, we need to kind of know a little bit how WinDbg works, and in this case there is an instruction or command which is called read MSR, and we need to specify the number of the MSR. And again, this is the number that I took from my blog post, and this is L star MSR. They all have, well, the address, I guess. So if you do that, it will give you an address in kernel, and you can tell that this is kernel address by the presence of the all Fs at the higher 32-bit part of the RIP. So, well, if we copy, unfortunately right click doesn't work, so I have to do Control-C and paste it into our disassembly window, we will get to the actual instruction in the kernel, or actual function that is being called. Now, if you know a little bit about system programming and kind of like the way syscalls are processed, since probably older Windows NT versions, they used to use KI system call, and it used to be 32, now it's 64, and then there's this shadow thing. again, if you read my blog post, it kind of explains all this naming and stuff. But basically, real quick, the shadow part is something that includes meltdown mitigation, and meltdown was the security flaw that was discovered a few years back. So anyway, that's the reason why it's shadow. In our case, it doesn't really matter. What matters for us is that we have this kind of like entry point into the kernel, and this is where we will need to set our breakpoint. Now, the problem for us is, well, several problems actually. First of all, is that we cannot set breakpoints anywhere over here. And the reason being is that, like, at any point, like during these highlighted instructions, we have our, well, two critical parts set up. Now, first, that is set up right here, is the GS register. GS register is used to point to a special kernel structure that contains most of the information for the kernel, for the current CPU core that is executing. So without GS, you can't do anything. And GS is like a special code segment, I guess, in 64, but it basically contains pointer to that internal structure. But we also need an RSP register, and all of that is needed so that our debugger, like a kernel debugger, could actually function. Because, technically kernel debugger is a process. It works, it's kind of like a part of the kernel, and I should probably say kernel engine. It's a part of the kernel that obviously has to do some work. So without having GS register and also RSP register, we cannot do anything. So GS register is set up over here by the swap GS instruction. But then RSP, if you see, they're doing a little bit of a kind of like they're using RSP here to set up page address table here for the meltdown mitigation. But it won't be ready until this point. So this instruction actually loads the RSP register for the kernel, and at this point we actually, we can set up our instruction or our breakpoint. Okay, well, there are technically two ways to set up a breakpoint in using WinDbg. The one would be just very simple, BP. Now BP, what it does, it literally sets up, I guess I should do it right here, it sets up an int3, it puts an int3, which is CC machine code, just 1 byte, at the address, so kind of like executes a software breakpoint with the int3 instruction. To make it more safe, I would use a BA command for WinDbg. This one sets up a hardware breakpoint, but for this we need to specify execution breakpoint and for 1 byte, and then we need to specify an address. Now the hardware breakpoint, let me just write it real quick. Hardware breakpoint is more reliable in the sense that you don't really change anything in the code. And I would probably use hardware breakpoint where, it's kind of like important piece of code. So let's use the hardware breakpoint. And as I just told you, we can set it up anywhere here. And if you want to, you can try to set it up on any of these addresses. And basically what will happen is that you will create a, blue screen of death, because again, debugger won't be able to function, and it would either hang up your guest OS, or most certainly it will create a BSOD. Okay, so if you copy the address and set up the breakpoint, so here you go. Now all we need to do is run. Well, we have to do it twice. There's something else here. And over here, as you can see, we're still broken into the kernel, but right now we are inside of a system call. So at this point we can step in, we can actually see the value of our registers. Now unfortunately, guys, this pane that contains all the registers doesn't really work well for me. It's really buggy. So the one way to kind of get the number of the values of the registers would be to use commands like R and the register, right? That's what I did. Okay, so as you can see, the SYSCALL has number 1A1. And this is totally arbitrary, because what we did, we literally broke inside the syscall handler, but not for our process, but for any process on the system. Now, if you look at the, at how many processes and threads are running on the computer, you will realize that there's a lot that's going on. Now, it's kind of interesting. I wish there was a way to do this, but if you could write a heat map of like address and memory, let's say for this one, or like for this, range of code, and kind of like could display with the color how hot this area was, or in other words, how many times it was executing code through this specific location, I can guarantee that this part of code would be the most called one. Because if you think about it, every single thread in the operating system, in the guest operating system, every single thing that calls a system API, which, there's a lot of them. If you just look at Win32, list, pretty much every single DLL inside System32, in some way indirectly calls to this function. And not from one process, but from everything running on the system. So this thing, if you continue on, let's say if I do, you see like RAX is totally different numbers. So in other words, this part of code gets called a lot. Right, so now it's 5, and if we do this, we get all kinds of system calls here with all kinds of different values. Well, the question is, how do you catch the moment when this instruction is called with our specific, with our specific request from our specific process? And this is when it becomes kind of tricky. So let me show real quick. Now, if you do BL, you can actually look at the list of breakpoints. Let me disable it for now and run. So at this point, our browser is misbehaving. Sorry, guys. But anyway, at this point, as you can see, our operating system is actually, a guest operating system is working. Well, how do you find a specific call from our specific invocation here? In our case, if you remember, we're calling wait for single object. So we need to have something that will limit it to our specific call. So what I suggest we do is that we unfold this instruction and use the one from the native world, and the one that I had pulled up earlier, and this one. Now the reason being is that we kind of like remove a couple steps and just make life a little bit easier for our reverse engineering. So because I'm importing this from from NTDLL, I need to link to NTDLL, and I need to link statically using one of these ways. In other words, this will be linking it to ntdll.lib, and this is the definition. So let me rewrite it a little bit differently. So again, it takes our handle, pretty much the same thing. This is not alertable, but then we need to specify it a pointer to a timeout. Now, what I was thinking originally is to specify something very unique value for this pointer, and then catch it with our debugger. And guys, just to iterate, I'm obviously talking about kernel debugger. So again, my kind of thinking is that when we get to this point in the kernel, we need to put a breakpoint somewhere here. That's what we did in the in the WinDbg. but we need to catch specific registers. Now the thing is, we can't really use anything from the user mode, because obviously we're really early at the entry stage, but we have our input parameters into this function. And what I was thinking is to replace this timeout over here with some unique value. Like for instance, if we do this kind of address, it will be quite unique for us to catch it, because not many programs will be calling, user mode programs will be calling wait for single object with this kind of address for our for the wait time. And again, the reason we can do this is because this NT native function has the third parameter that gives a pointer. Now the question is, how would we do this? Well, we can just pass it in like this, right, and just convert it into large integer, and this would work for us to catch it. But unfortunately, it will create an exception, and it will, this function would not work. So let's do it a little bit in a little bit clever way, and we can actually request for the memory manager to provide this address for us. And this looks like a user mode address, so it should be able to do this. Now if you remember, you can actually do this with the virtual alloc function, and let me kind of quickly show you. So if you go with the virtual alloc x, it takes a few parameters, like for instance, we obviously need it in current process. Now then, the next parameter is the address that you are requesting, and in this case, let's just do that. And while I'm thinking, guys, it's probably too large of an address. Let's remove like something from this, for instance, like so. Yeah, so we don't go too far from the base. And again, so the third parameter, second parameter, would be the address that we want to ask. And if you know how virtual allocations work from the user land, what it will give us is that it would cut off these like initial bytes here, and just give us, it will align it to the page size. So we will need at least one page size full of data, in other words, to account for this part. And then we need, let's see, memory commit, and also memory reserve to kind of get all of it. And let me break it up like this so you can see. Okay, and last thing, let's see, what is it? Oh, protection, and this is page read write, because obviously we need to read into it. And over here, well, we just get some kind of address, and obviously we need to call it right. Okay, so in this case, if the memory manager is cooperating and gives us an address, we will get it here that we can use. Now in case it does not cooperate, we can just do printf and just say error. And just for, because we won't be running, well, again, just to give some basic kind of like error handling here, we'll just output the error in case we do not get the address in this page. Okay, but obviously we're not interested in this part. But if we get here, we need to modify our address. Let me show you what happens. So if we run this thing in the debugger right here, just to kind of like illustrate the thinking here. So if we run, oops, what did I do? Oh, sorry. Is it like SDL here? So again, let me run, make sure it runs. Okay, so again, guys, if we get to this point and execute this instruction, as you can see, the address that we got is with like last four zeros cut off. So in other words, if it gives us the address, we need to adjust it to what we wanted here. And because we got the whole page, so it shouldn't really matter for us, as long as we are within it. So what I suggest we do, just basically OR our address with this kind of thing, and we need to coax C to actually do it, because again we have a pointer here and not the size T, so usually you shouldn't be doing this kind of thing with pointers. But for our case, if we do this and then pass it into our function as a pointer to large integer, right? Oh, obviously need semicolon here. So this should technically give us that specific address. You see, like 11224455, and then when we execute our wait, now the wait function obviously will return an error. Well, let's see, what would it do? So if we do nt status, oops, what am I doing? Okay, here it goes. Test. Guess it helps if you can type. And let me just do something over here so I can just check. Okay, so let's see if we run it. Okay, the status actually, the operation expired because, we probably had zeros at that address. And if you look at the documentation, this last parameter here is the value of a timeout. Well, in this case, we don't really care about the value of the timeout. What we cared is this special address that we are passing into our system call, right? And then we can actually use our logic inside. Let me show you where is the inside. Inside of our SYSCALL machine code or assembly code to actually catch the moment when our register, in this case the third register, is this specific value. Now before we go into that, let's see which register would it be. Now if you go into x64 calling convention, and obviously Microsoft calling convention, you can see that these registers, just copy them into our cheat sheet. So these registers would be used to pass the first, second, third parameter. In our case, we are concerned about the third parameter for the function, right? First, second, third, that will contain our special address. So let's copy it into our cheat sheet. And so we need to catch is when our 8 is equals this kind of madness here, right? Now, that alone might not be enough. We also need to make sure that our RAX, or the register that is used to signal the syscall, is specific for our invocation. Now, if you look in my blog post, I actually did this work already. And for NT wait for single object, the RAX, or its lower 32-bit cousin, is 4. So what we need to catch here is when our RAX is 4. So if we have this kind of a condition inside the kernel, again I have to scroll down in my blog post, inside the kernel here, in other words, when RAX is 4 and R8 is this special address, we can technically catch that specific syscall that we are making from this function, right? Well, so let's try to do this. And before we do that, let me build another release build of our test project, because again we modified it, so now we need a new version. And I think it's still open here. Let me make sure that the timestamp is correct. Yep. So I need to copy it into my virtual machine. And before I do that, I need to close IDA and copy it here. So right now when I run it, it will simply go through and run, because if you remember we would change the timeout. So right now it's probably 0, so it just doesn't do anything. And at this point, let me just put it back into IDA and kind of quickly step through it so that we get to the SYSCALL. This part is just basically repetitive, so there's not much going on here. As you can see, there's a little bit of a difference here. So we need to put a SYSCALL breakpoint here, run it, and let's hope that the memory manager cooperates, and it does. So let's quickly step through, and as you can see, this is our SYSCALL. This is the value 4. And again, what is happening now, if you just try to step into it, nothing will happen, and then we'll return back and continue. So this is not interesting. So let's try to catch it from the kernel. Again, let me repeat it again. Step in and get to here. So again, here's the SYSCALL. As you can see, the value of R8 right here where I'm pointing with the mouse is our special 11224455, and RAX is 4. And let's get back to the kernel debugger. Let's break the guest OS, do BL, and enable our breakpoint and run. Okay, so at this point you see that we broke, but obviously we broke on some SYSCALL that is not what we need. Now there are several options to go here. The one that I would definitely not recommend is actually setting up a conditional breakpoint in WinDbg. Now in most cases that would be a good way to go, and again you can put like a couple conditions for, you know, these two registers to be these. The reason it wouldn't work, and I'm not going to demonstrate it here, just kind of trust me. If you want, you can test it yourself. But the reason it wouldn't work is because this part of code, like I said, is called so many times from so many places in the operating system that if you set up your conditional breakpoint, what will happen is that, well, your operating system, the guest operating system, will grind to a halt. You won't be able to do anything. It will kind of work, but kind of not. So conditional breakpoint definitely wouldn't cut it. And the reason being is that internally, WinDbg will attempt to run a lot of JavaScript to evaluate your condition. And as you can imagine, this code has to be very streamlined and optimized to actually work, you know, perfectly, because it, I mean, efficiently, because it's invoked from many places. So yeah, conditional breakpoint unfortunately doesn't work here. But what will work here is a kernel patch. As you can see, there are some instructions here, and what we can do, we can actually put a little bit of a code here. So if you remember your x86 assembly, if we can somehow check RAX for being 4, right? And then let's say if this is not the case, let's just say like label no, right? And label no, in our case, will be just continue, right? And then if RAX is actually 4, which would not be enough because we'll catch all the invocation of the NT wait function. Second thing that we need to do, we need to make sure that our RAX is this instruction, and if it is also no, then we continue. So this no thing is just basically continue on, right? So do whatever you want. And then over here, if we put a NOP instruction, this NOP instruction will execute only if these two registers are what we want here. And then if we put a breakpoint on this specific instruction, we will actually step into the kernel right from the moment when we invoked it from our NT wait for single object from the user mode. Well, but how do we do this? We obviously need to include this stuff somewhere, and as you can see, there is no space here for us to do that. Now, the most conventional way to do this is to replace one of these instructions. As you remember from my previous description, we can't really do anything here, but we can once we get the kernel stack here with this instruction, with this move instruction. Now, the way we do this is that if we have, just kind of copy this thing quickly so I can demonstrate. So if we have our original instructions, right, like over here, let me just kind of do this in Visual Studio. It has a little bit better editor. Okay, so if we have our instructions, let me remove all this. Right, so this is what we have in a kernel. And to make it more user-friendly, let me leave just the machine code. So if we remove one of these instructions and make a jump to our conditional check here, right? So if we do, let's say, label check, right? So if we put a jump, let's say instead of like this instruction or this instruction, if we just put a jump to our check, right, so it will execute all of our check and then come back and start working like the actual code. Well, obviously need to make sure that we don't overwrite any instructions, and in this case we don't. We just check them. As you can see, it doesn't change any registers. And I'm sorry, don't overwrite any registers. Okay, but jump check is not really something that that we can put here, because again there is no hole. So what we need to do, we need to ensure that we can use one of these instructions and put the jump instead of it. So before we go any further, we need to see how long is the jump instruction, in other words, how many bytes it takes. So I personally use this online disassembler. I personally like this one. Again, it's your personal preference. You can use a different one. So for instance, if we do jump, just some long number. And as you can see, a jump instruction, in this case, would take 5 bytes. And let's see, so jump would technically take 5 bytes. So we can't use this push instruction, but we can use this one. So if we take this one out, just take this out and put it here where we do our continue, right? And then we need to jump back, and label back would be this thing, right? So instead of a push instruction, just kind of like comment it out, we will use our jump to our check. Again, it's kind of confusing at this point, but let me just explain real quick. So, right, so instead of this push instruction, we'll put our jump to our check, then we will execute our check, right? We see like, okay, is Rx this, is R8 that? If no, label no, we obviously have to do our push, I mean Microsoft's push that they had here, and then jump back to this instruction. So it's kind of like a trampoline, I guess, if you want to call it that way. But before we do anything, we need to ensure that our jump instruction has the same length as the original instruction. As you can see, it does not. So we have to add 90, and if you remember, 90 is the instruction for no operation. Again, you can kind of check it here. If you do no operation, so you can see 90 hex is the actual no operation. So what we're doing here, again, we have to match the length of a jump exactly to the length of the push instruction so that, it doesn't create a gap. And then over here, obviously we don't know how far we're jumping. Let's see, I need to make sure. So 1, 2, 3, 4. So these CCC would be the actual offset where we're jumping, because at this point we don't know. And then we've just padded with a bunch of no op instructions. And remove this guy. So, and this will be our patch, kind of like, again, just in text form. We'll execute this push instruction, again, because it's not long enough to fit our jump. Then we will do our jump to our check. And then we'll check is RAX 4. If no, we go to label no, and label no will execute the push that was supposed to be here. And then we'll just jump back to our next instruction here. And also, like, for instance, if RAX is 4 for the correct syscall number, then we check if R8 is our special address that we're trying to set up here from user mode. And if this is the case, if this is not the case, again, it will go to push and continue on. If yes, it will execute our NOP, and this is where we put our breakpoint. Okay, so this is kind of like the thinking. And the only thing that we have left to do, well, to patch the original sequence in the kernel, but also find some space for this stuff. And to do that, we need to go back to the kernel. As you can see, we're still broken into the in the shadow system, system call 64 shadow. And let's scroll down and let's see if we have any room. So right here, as you can see, there are instructions. I'm literally just scrolling down. And what usually happens is that the compiler pads every function on certain boundary. And as you can see over here, at this specific address, we have all these zeros. And this is more than sufficient for us to put our little patch. So before we do that, though, we need to see how far, what is the machine code that we need here and how many instructions we need. Obviously, if you look here, there's way more data, way more bytes available than we will probably need, but just in case, let's see how much do we need. So this one, obviously there is no bug, so we're just gonna write something here and let's try to assemble it. Oh, sorry, it doesn't like comments. Oh, and also there's a different syntax for the hex numbers. Okay, so this is technically, the length of our machine code, and it's not a lot, so we can definitely fit it in there. And let's look at what the assembly language had given us. So E means the offset from here, and we jump to this instruction, which is 14, so it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, so we get to this byte, which is correct. And the same here. So yeah, that should be okay. The only thing, okay, this part is kind of interesting. Let me check. Okay, guys, yeah, I had to look it over. As you can see, there's a typo. And this is very important because, as you can see, this instruction is not what it's supposed to be. You have to obviously check all this stuff, because otherwise you'll definitely create a blue screen of death. Again, it was a typo, and for some reason it decided to take the label that didn't exist. So let me try it again. Okay, so now it's way more interesting. So as you can see, 75 mnemonic is the short conditional jump, and it has to be exactly as this one with a different offset. Let's check the offset. Again, A is 10. It starts from here. Let's just count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, we're jumping to this byte. In this case, the offset is 1, which is the length of 1 byte here. This is correct, and this will be the long jump. And so far so good. So let's copy this thing, and over here let's correct it. Let me go back to our notepad and change it like so. Okay, so two things we need to know is this offset and also the offset initially where we are jumping from, like this stuff. So again, let me put it into one spot. I'll put it into my cheat sheet here. Right, so in other words, this part, how far we're jumping, and also this this part, how far to jump back. Now for that, let's get the address where we will be putting this in the kernel. Now I will try to align it on 16 bytes. That's why I wouldn't be using this one, but instead I will use the next one. And let me put it down here. So this is the address. Let me make sure I copied it correctly, because that was the problem in my previous tutorial. So 133E0. So it's important that we calculate all these offsets correctly. And then if we go back, we can probably just scroll up. Now if you look, let me just copy all these instructions here the way they are. So we have addresses. Okay, so if we look, this is the instruction that we will replace. And the address of it is this. And then we will have our instruction here. Right, so let's just split it up in bytes. So in other words, when we do our patch, our jump will have this mnemonic with the replaced CCC values. And what we need is to calculate the address of the next byte that follows to get us the offset. And as you can see, this one is F. This one is 0, 1, 2, 3, 4. So if we just do it kind of quickly, this one would be B4, the address of this instruction. And then we need the offset from B4 into this one. And the easiest way to do this is to use a calculator. We just do subtract this one. It's important again to calculate it correctly, because if you make a mistake, that will be a problem. Okay, and the offset is 22C. And let's do like so. And if you remember the way x86 instructions are encoded, it's like little endian. So 2C goes here, and 02 goes here, and the rest are zeros. Again, this is the lower part goes here, and then the next byte goes here. Let me just double check. Okay, yep, this is correct. So this will be our encoding for the jump instruction, right, from the original, from over here. So, and at this point we can actually patch, because again we have the kernel stopped, so nothing works. If you remember the way to patch, let me put like a real quick here, the EB, I know it's kind of confusing, EB instruction in Win32 takes the address and then bytes. So it basically writes these bytes at this address. So, and what we can do, we can just prepare it here. So we need to do EB at this address, And this address, if you remember, is the address of this instruction that we are replacing with the jump. So let's just do so. And what we are doing is that we need to write this into it, but we also have to match the length of it. And the easiest way is just to align it like so in Notepad. And again, I've done this before. I'm kind of like stepping through this real quickly, really slowly, so you guys can follow it. And we already had done that, so basically we need to pad it with nulls, right? And this is what we need. So let's copy it into our debugger and execute. Okay, so over here, as you can see, right after we executed our sequence here, the debugger was, disassembler was smart enough to give us a jump. And the jump right now goes to this instruction, which doesn't have anything. So now we need to actually put our machine code. And before we do that, we need to calculate this offset. And the offset has to go back to our address here, right? Remember, like we put a patch, so now we need to come back to this push R11 instruction. Well, let's kind of do a little bit more math here. So let's just say jump 2. And over here, the disassembler gave us kind of like virtual, like fictitious addresses for this little block of code. And if you look at it, obviously it shows it in hex, so it's 8, 9, A, B, C, D. So the next one is 1D. Right, so this one is D, but if you remember, the actual address is this thing here in the kernel. So what we have, jump from, so we need this plus 1D. So the easiest way to do it is just to copy it in the calculator. Make sure to switch it to programmer in hex. I need to make sure I copied it correctly. 3330 plus 1D. Okay, so this is that. See. Okay, so we're jumping from here to here. This was obviously a negative jump, so let's just do FFD minus this minus 246. You know what, the easiest way probably would be to do this. Just reverse the order so the calculator gives us the negative value, because again we're jumping back. If you remember, we stepped forward, that's why we have to go back. So this is our offset. And so very easily we kind of have to put this thing in here, and if we break it into bytes, that will be this. And again, since Intel is little endian, so we have to do it in reverse. Oops, FF. So again, this goes here, this goes here, this here, and this here. So this hypothetically should be our offset, right? Okay, and then the last thing we need to do, we need to create a command for the WinDbg to actually write all this stuff at this address. Right, let's make sure that this is the correct address. Yep. Okay, so we just have to copy and paste all of this. Not very interesting for you guys, so just bear with me. It's just these several lines. It's important to copy everything and not miss something, because if you miss, you'll definitely crash your operating system. Okay. Yeah, that will be a little bit long line here for one line in Notepad, but bear with me. Okay, so let's see what happens if we put it into our kernel. Okay, as you can see, it looks a little bit confusing when I quickly jumped. But this stuff here should technically be our patch that we need, like this stuff. Let's just step over, not step over, look over with the debugger. So if RAX is 4, if not, we jump to this address, which is correct. Then we check R8 for our special number. If no, we also jump to this address. Eventually we do our push and jump back to this address. So yeah, it seems like this is correct, right? It's 31BC. We need to make sure that the offsets are correct. And 31BC, and yep, so the only thing we need to do, we need to remove our current breakpoint and put the one over here. So we do breakpoint. This time I'll use the software breakpoint. Okay, so we put it on our knob. And let's scroll back up. So yeah, let me step into. Okay, so RAX is not that. It does push. It comes back and continues on. Well, guys, if I let the debugger run, it should technically run without breaking. Let's make sure that our operating system is still functional. Okay, I have to minimize all this stuff. Okay, so as you can see, we are still functional. And let's try to step into our SYSCALL from internal user debugger. Let's see what happens. And this is the SYSCALL. And here we are. As you can see, the debugger started flashing, the kernel debugger started flashing. So now, if you look at RAX, it's 4, R8, oh, I'm sorry, R8 is our magic number. So right now we broke exactly into our call. If you remember our NT wait for single object from user mode, and we are in the kernel actually processing this call. So right now you can actually step in, kind of keep going with the debugger, and this is exactly how I researched it and how I was able to catch what is happening with the debugger. Now this part is again a little bit out of the scope of this blog post. Again, this video is kind of long for now, so you can kind of see that you can step through most of the functions here, and let me just show you real quick. So yeah, debugger is a little bit slow, but then when you get to here and get to this point, let's see, there should be a call to the actual kernel function, and it is done with RAX. So yeah, we do like jump through this stuff, and yeah, this part here is when we get to the actual kernel function that processes, the actual kernel call. Again, guys, this is not about stepping through the kernel and understanding how it works, but this is basically how you step into kernel from user mode with kind of two debuggers. And last thing, let me show you, if you let this debugger run and then switch back to your user mode, we're back in the user mode, and we just stepped into the kernel from a user mode debugger. Okay guys, again, this was kind of long. I rambled along a little bit, but this is a basic explanation how you can step into SYSCALL with a little bit of a kernel binary patch and the use of two debuggers. So thanks for watching, and I'll prepare something interesting the next time. Thanks.